Well, hello. While this is loading, I just wanted to introduce what we're going to be talking about today. Last week we did lesson 5, which was about dropping objects and the effect gravity had on them. Today we're going to be talking about what happens when we launch objects. And so we're like throwing a ball up in the air or something like that. And so that's what today is going to be about. So we have here first the cannonball here. It says a cannon is 10 feet off the ground. It launches a cannon straight up with a velocity of 406 feet per second. That's important. So imagine there's no gravity. That means it doesn't come back. It's still going away and away and away out into space. And every second it's going 406 feet. That's what 406 feet per second means. So you can see here in this first one that I clicked, if it starts at 10, then in 1 second, it's got another 406 feet. So that's a total of 416 feet. Then another 402 seconds, another 406 feet is 822. Another 406 feet is 1,228. Another 406 feet is 1,634. Another is 2,040. So how do we get that end for t seconds? Well, what are we doing? Every time we're adding 406. So for the number of seconds, in 2 seconds, it's 812 that I am adding. For 3 seconds, it's 1,218 because that's what 406 times 3 is, and so on. So we end up with 10, our start number, plus 406t, t being the number of seconds. So the equation that represents that is, is going to be d equals that t 10 plus 406t. D equals 10 plus 406t. So now we're looking here and now we say, okay, now what? It's saying it already gives it to us. This is with gravity. Flip the switch. Gravity's back on. This is the table that we have now. What does that mean? So you can see at 1 second, it's only 400. It only went up by 390 feet. In 2 seconds, it only went up by 358 feet. In 3 seconds, it only went up by 326. 4 seconds, 294. 5 seconds, 262. So what are the observations that I can make? Well, that first table seems to be increasing faster. In 5 seconds, it increased more. And then table 2 does not increase at a constant rate. The other one's increasing by 406 every second. This one is not. You can see that those times are going down. So if I'm going to graph this, and I'm looking at this particular graph, so I've got my time in seconds on my x-axis and my distance above the ground, or we call that a lot of times height, on my y-axis, we end up with that. So how are they alike? Well, they're both increasing. How are they different? Well, the blue with one where I ignored gravity is linear. It's going up in a straight line. And you can see that the actual height's not so much. It kind of still looks like it's linear, but the fact that it goes from that first point near the origin to the second, it's not quite the same. And we saw from the table that those distances were not the same. So we're going to talk about what's going on here. So number 3, write an equation to model the actual distance of the ball after it's fired from the cannon. Well, the only thing I need to add let's go back, here, this 10 plus 406t is gravity. Because I need to add that gravity piece to pull it back to the earth. And we got that when we talked about the dropping, and that was the minus 16t squared. So that's where that comes from. So that equation, let's go, here we go, should be the d equals, and then we've got the 10 plus 406t, but the minus 16t squared from the gravity is what brings it, not make it increase as fast. And then once it reaches its maximum height, then it's falling again to the earth. So this question is saying, we've got a new cannonball. So it's graphing another one. The function defined by d equals 50 plus 312t minus 16t squared gives the height in feet of a cannonball t seconds after it leaves the cannon. So those 3 terms again, similar to what we just talked about. 50 represents that starting height. Where did it start? Started at 50. So it's 50 feet off the ground when it leaves the cannon. The 312 represents the speed at which it was shot, like the 406 feet per second. This is 312 feet per second. So 312 T is how far it would have gone in T seconds after it left the cannon, if there was no gravity. But since there is gravity, the minus 16 T squared is that gravity bringing it back to Earth. So this number 2 here that you see says use the graphing technology to graph the function using that window. So I did that. I went to Desmos, and I want you right now to pause your video, go to Desmos. When you open Desmos, put in that function, the d equals 50 plus 312t minus 16t squared. And then what I want you to do is go to the wrench and make your x intervals. So when it has that inequality with the x's, make the one on the left 0, the one on the right 25. For your y's, the one on the left 0, the one on the right 2000. And then you'll see that full height graph. So I want you to do that right now. I'm going to pause. I want you to pause the video while you do that, please, for just a moment. Okay, so if you have done that by now, you should see something that looks a little bit like what we're going to see here, like this. It's going to look slightly different, and I have that screenshot of that here in just a second, but it should look similar to that. And it says describe the shape. What does that tell us about the movement of the cannonball? Well, this represents the height, the distance off the ground, the height of that ball. So it reaches a peak and then it decreases. It goes up, reaches a peak, kind of seems to, if you're familiar with balls at all, kind of hangs there for what seems like a second, then it comes back down. Okay. Went up in the air and then came back to the ground. And then the next two questions says estimate the maximum height and when does it get there? And then when does that ball hit the ground? So on your graph should look like this. And what you're looking at here is this number way up at the top. Okay. That means that if you look, your x is your seconds, so 9.75 is the number of seconds. Your y is the distance in feet, so 1,571 is that distance in feet, the height of that cannon. So the cannonball will reach its maximum height of 1,571 feet above the ground in 9.75 seconds. And then when is it going to hit the ground? That is over here. That's when the height is 0. Remember, it's height above the ground. So if it's on the ground, then the height above the ground is 0. So you're looking for where it's going to cross that x-axis. So that's at about 19.659 seconds, just slightly less than 20 seconds, not quite. A little bit more than 19 and a half. So now we're looking at the summary. So we have this function, all right? The object is thrown upward, initial height of 5 feet, 60 feet per second is its velocity. So that minus 16t squared is the gravity. So h of t equals 5 plus 60t minus 16t squared. The 5 plus 60t represents the height if there was no gravity. And in t seconds, how 2 seconds, 3 seconds, 4 seconds, if there was no gravity. But there is gravity. So the minus 16t squared represents that effect of gravity. And then we've got the graph of this. The graph intersects the vertical axis at 5. That's your y-axis at 5 because it's the initial height. And then the graph indicates that the object reached its peak height of about 60 feet, a little more than 60 feet, in a little less than 2 seconds. You can see where the peak is there. We call that the vertex of the graph. And we can see that it hits the ground between 3.5 and 4 seconds there, a little bit more than 3.75, it looks like. And then we call this a parabola. So you're going to learn about the geometry of that. And we're going to keep talking about this whole unit. This next 2 units that we're going to be studying until the end of the year is all about quadratics. And this is just the beginning. So what you're going to do next is you are going to do another fill in the blank, similar to what you did one day last week with this. So this is on that document. So use the document and do the fill in the blanks from the summary. And then you can be done, call it done for the day. So I am glad that you joined me today, and we will talk with you tomorrow.